This is section 2.4, the chain rule. The chain rule is probably one of the most powerful and useful rules for differentiating that we're going to encounter. And it's going to take us to being able to the level of being able to do all kinds of things we couldn't have done before. So if you look at the two columns without the chain rule and with the chain rule, it's about the third or fourth slide. On the left, you can just do those derivatives right now. You don't need the chain rule. But if you look at the ones on the right, those are mostly, in fact, every one of those is a case of a composition of functions. It's not just x squared plus 1, but it's the square root of that function. It's not the sine of just plain x, it's the sine of a function of x, 6x in this case. It's not just a linear polynomial 3x plus 2, it's that raised to the fifth. So, and then of course the last one, tangent of not just x but x squared. Basically what the chain rule does is it allows us to, or it states that if y is changes dy du times as fast as u, and u changes du dx times as fast as y, then y changes dy du times du dx times as fast as x. For example, look at example 1. A set of gears is constructed as shown in this figure, such that the second and third gears are shown on the same axle. As the first axle revolves, axle 1 revolves, it drives the second axle, which in turn drives the third axle. Let y, u, and x represent the numbers of revolutions per minute of the first, second, and third axles, respectively. We are to find dy du, du dx, and dy dx, and show that dy dx is equal to dy du times du dx. So axle 1 has a speed of y revolutions per minute. For axle 2, it's u revolutions per minute. And for axle 3, it's x revolutions per minute. Okay. Now, if you look at the radii, that's actually important for each gear. Look at this, that the circumference of the second gear would be 3 times that of the first. The first axle must make, because of that, the first axle must make 3 revolutions to turn the second axle just 1 time. Similarly, the second axle must make 2 revolutions to turn the third axle once, and we can write the following, that dy du is 3. And that means that, again, that's the first axle must make 3 revolutions to turn the second axle once. And du dx would be 2. Again, that's the second axle must make 2 revolutions to turn the third axle once. Combining these two results, you know that the first axle must make 6 revolutions to turn the third axle once. So we can write dy dx, which is the rate at which y is changing with respect to x, is the rate of change of the first axle with respect to the second axle. Oops. Respect to the second axle. Multiplied by the rate of change of the second axle with respect to the third. which is the rate at which y is changing with respect to the rate at which u is changing, multiplied by du dx, which is the rate at which u is changing with respect to x. And because of the constants we have up above, that's 3 times 2, which is 6, which gives us the rate of change of the first axle with respect to the third axle. In other words, the rate of change of y with respect to x is the product of the rate of change of y with respect to u and the rate of change of u with respect to x. What makes me feel like this is an easy to understand thing is, at least symbolically, is if you were to look at this line right here, this statement, if the differential were something that could be just canceled because they're the same, we could cancel this du with that du, leaving dy over dx, which makes sense. And so I think that's a pretty easy thing to understand. Now, that's usually not the way that I think about doing this myself. So what I'm going to write this as is, and I'm actually going to go to theorem 2.10, and the second half of it is the way that I usually will think of this. If we have a composition of functions, f of g of x, then the derivative of that composition with respect to x is, you follow the rule of the outside function's derivative rule. So if the outside function, well, I'll give you an example in a minute, but we're going to take the derivative with respect to the outside function's rule and evaluate it at the inside function, and then we're going to multiply that by the derivative of the inside function. Okay, and that's equivalent to what you see above in the Leibniz notation, but I find this one to be a little bit more user-friendly. And so that's the way that I would like to always present this. So one of the first things we're going to have to do is make sure that you can identify the inside part versus the outside part. Because the outside part, you're going to take the derivative rule for the outside part, evaluate it at the inside part, and then multiply by the derivative of the inside part. Okay, so that's the kind of the process we're going to be going through. So let's look at example 2, and what I'd like for us to do in each case is, given a composition of functions, this is a general thing that we're going to see for each of these, identify what the inner function is and what the outer function is. Okay. So, in this first one, y is equal to 1 over x plus 1. In this case, the inside function is the x plus 1. And our function is 1 over something. That's the outside function, is 1 over something, and x plus 1 has been plugged into that something place. You can hear me say something a lot. Usually that refers to the inside function. Okay, so now we have y equals sine of 2x Well, that outside function, in fact, I usually truly do this one first in my head. We're taking the sine of something, and that something happens to be 2x. So a lot of times I identify the outside function sort of first in my head, and so I'm going to probably write them down in that order, if that's okay. Hopefully it is. All right, so try this one without my help. I'm going to write it down and then pause the recording and see if you can identify the inside and outside function. Okay, for me, the outside function is that we're taking the square root of something. And that something is a polynomial, 3x squared minus x plus 1. Okay. And then d. Try this one as well on your own. So after I've written it down, pause the recording and see if you can come up with the inside and outside function. All right. My thought is that we're squaring something. That's the outside function, is the squaring function. And what we're squaring is tangent of x. Okay. So let's go ahead out here to the right. I'm going to add something that doesn't actually say to do, and I'd like for us to find y prime in each of these cases. Okay. Well, the derivative of 1 over something is going to be, well, first of all, let me write something over here. We'd want to think of that as u to the negative 1 for derivative purposes. So the derivative is going to be the rule for the outside function, which is the right-hand column, is we're going to take negative 1 times our something and decrease the power by 1. Then we're going to multiply by the derivative of our inside something. So this is going to be negative 1 over u squared, and remember our u was x plus 1, times the derivative of x plus 1, which is 1. So our final answer is the opposite of 1 over x plus 1. Squared. Oh my gosh. I forgot to put the square on that. That's what I did wrong. So x plus 1 squared. Yikes. Not a good thing to mess up. Okay. Let's see the next one. The derivative of sine of something is cosine of that something times the derivative of that inside something. So that will be cosine of 2x multiplied by the derivative of u equals 2x, which is 2. And so our final answer would be 2 cosine of 2x. Okay, the next one. The derivative of the square root of something is, well, let me write this over here. We'd want to think of that as u to the 1/2. Will be 1/2 times that something to the reduced by 1 power times the derivative of the inside something. So that's going to be 1/2 u, which is that trinomial, times the derivative of that trinomial, which is 6x minus 1. And then simplifying, that would be 6x minus 1 over 2 times the square root of 3x squared minus x plus 1. Okay, and then the last one, I'm actually going to move over. Well, I'll move down. It's okay. That'll be sort of consistent. So the derivative of something squared is 2 times that something to the first times the derivative of that something. So that'll be 2 times tangent of x to the first multiplied by the derivative of tangent of x, which is secant squared x. And so our final answer is just that, 2 tangent x secant squared x. Okay, so we'll practice this a lot in this section so that you get really good at it, I hope. And one of the things that's going to happen quite a lot, and in fact I think it happened 3 of these 4 times, most of these were treated as powers of something, u to the negative first, u to the 1/2, u squared. And so there's something called a general power rule, which is just basically a special case of the chain rule. Says that you're going to bring the old power down in front. You see how we did that for like the first one, -1, times u to the reduced by 1 power, times, they say du dx, and I had written u prime. Doesn't really matter which of those notations you use. And you see down below, that's basically what I did. Okay, that's a general power rule. So let's find, for example, 4, I think is the number of this one. If I have f of x equals 3x minus 2x squared quantity cubed. Please keep in mind, if you wanted to, you have alternatives a lot of times, and this is one of the times. If you wanted to, you could multiply that binomial times itself and then get that answer, multiply it by the same binomial again. In other words, do the cubing, get a polynomial answer and take the derivative of that polynomial answer, and that's perfectly legitimate. And that wouldn't be bad with cubing. You might make some mistakes along the way because you might not be as good at cubing a binomial as squaring. But if I were to raise that to the 31st power, I hope at that point you're thinking, no way do I want to do the raising to the 31st power, multiply that by itself over and over and over and over and over again, and then take the derivative of the result. So even though this one could be done the other way, doing the cubing, I think using the chain rule is going to be a whole lot better. So you don't necessarily have to write down what I'm about to do. You could skip this and do it in your head, but I want to write it down this first time. The inside function needs to be identified, even if just inside your head. And you need to identify what the outside function is. It's the cubing of that inside function. So the derivative here, looking at the outside function as cubing, will be 3 times whatever is inside to the reduced by 1 power, then multiply by the derivative of the inside something. The derivative of 3x minus 2x squared is 3 minus 4x. And as I've mentioned a couple of times before, I really don't want you to distribute this. I want it to be in factored form, mostly because of something that we're going to do with it coming up very soon. It is common to write this in increasing powers. So I put the 3 minus 4x, which is to the first, after the constant 3, and then after that came the binomial squared. Okay, so there's that answer. So let's see how we do with a few more of these. Let's see, the next one I want to do is what if f of x is x squared times the square root of 1 minus x squared? Okay, so here we go. First thing is, radicals are not our friends in derivative processes, so I'm going to suggest that we rewrite that as 1 minus x squared to the 1/2. Okay, first thing I notice is that the big idea of this problem is it's a product, so we're going to have to employ the product rule, and that will be first function times the derivative of the second. The second one is a composition. We have something to the 1/2. So our derivative of that will be 1/2 times that something to the reduced by 1 power. Then the chain rule kicks in, and we have to multiply that by the derivative of the inside something. The derivative of 1 minus x squared is negative 2x. Okay, so that was first times derivative of the second, plus second times the derivative of the first, which is 2x. Okay, so because factored form is so useful in an upcoming application, I'd like to talk a little bit about that right now. But first, let's do a little bit of simplifying. Before we do that, factoring. The 1/2 times the 2 is going to become 1. And then we have the negative, so let's put that out in front. Then we have x squared times x, which is x cubed. And the only thing left is 1 minus x squared to the negative 1/2. Plus, and then I'm going to pull the 2x out in front of the binomial. Usually write monomials before binomials, raised to various powers. Okay, so now let's factor. Looking at this, there's no numerical common factor. If that 1/2 hadn't been up there above and we'd still had a 2x, we would have pulled a 2 out as a common factor. But that 2 and the 1/2 canceled, so that's not an issue. So the next thing I see is that we have a common factor of x to some power. And I want to ask you, if you recall, when you have various powers of x, which power of x is the common factor? It's always the lower power. So the lower power of raised to the third and raised to the first is to the first. So x is a common factor. And so keeping that in mind, what power of the binomial is a common factor? Is it the negative 1/2 or the 1/2? Well, it's whichever one's smaller. And any negative number is smaller than a positive one. So to raise to the negative 1/2, that's the common factor. Okay, so if we factor out both of those things from the first term, we'll be left with a negative sign, and x cubed divided by x leaves x squared inside, and 1 minus x squared to the negative 1/2 divided by itself leaves a 1. I won't always write that times 1, but I just want you to see where things were headed. Okay, now, next, 2x divided by x leaves 2, and okay, sorry, was interrupted there for a second. Now, dividing 1 minus x squared to the 1/2 divided by the 1 minus x squared to the negative 1/2, that's division with the same base. That means we keep the base, 1 minus x squared, and subtract the exponents. 1/2 minus negative 1/2 is 1. And again, I won't always write that 1 as a power. It's understood, but I want to write it here for clarity. Okay, and if you have trouble with that, this is a good thing to ask about in class, this factoring with various fractional powers and binomial common factors and all that kind of stuff is all good, and it's stuff that you should ask about for sure. Okay, if you don't get it. So negative x squared times 1, of course, is the opposite of x squared. Then if I distribute that 2, I'll get a 2 minus 2x squared. Then I would say we should probably collect like terms inside of the last set of parentheses so that it is completely simplified. So that's going to be 2 minus 3x squared. And of course I could have written negative 3x squared plus 2 if I'd wanted to, but I, unlike some of your algebra teachers from high school, am not so hung up on the polynomial having to be written in descending powers of x. I'd rather have the first thing be a positive thing so I don't have a negative sign out front. That's just my own little idea of how this should look. Then the last thing, remember when you have negative exponents, generally speaking, that's not something we want to keep as a negative exponent. So that negative exponent will be something that we take down into the denominator to get rid of the negative on that exponent. And because it's raised to a negative 1/2, 1 over something power, I want to always ask that you rewrite that as a radical. If it's 1 over something, like if it had been 1 over 3, it would have been a cube root radical. If it had been 1 over 4, fourth root radical, etc. Okay, so that is the final answer for this one. Okay, let's move on to another example. What if we had f of x equal to x over the cube root, speaking of cube root, of x squared plus 4. Okay, so the first thing I'm going to do is rewrite so that I don't have radicals. Our answer may very well have radicals in it. Like the example, you can see the answer right above this one. But for derivative purposes, that's really not user-friendly. So rewrite that as x squared plus 4 raised to the 1/3 power. The big idea of this problem is I see a quotient, and so that means we're going to do the quotient rule. So that is low, that is denominator function, low, d high, and the derivative of x is 1, minus high, the numerator function, d low, the derivative of the denominator function will be, because it's something to the 1/3, that'll be 1/3 times that something to the reduced by 1 power, so negative 2/3, times the derivative of that something. That's the chain rule kicking in. That times 2x right there. That's the chain rule part. All over the square of low. Squared. Okay. And like I said at least once before, if it's a complicated problem, you should probably kind of in your head go back and look at it and make sure you did do low, d high, minus high, d low, all over the square of low. It's very easy to get caught up when it's complicated and forget one of those steps. So that would be something you'd want to look out for. Okay, so the first thing I want to do is simplify as much as I can. Let's see, that will become 2/3, 1/3 times 2, x squared, x in front times the x at the end. Okay, that's all the monomial stuff, times x squared plus 4 to the negative 2/3. And then powers on powers means that you do what to those exponents? Right, you multiply them. 2 times 1/3 is 2/3. Okay, now factored form. the only common factor we have is x squared plus 4 raised to some power is our common factor. Which power is lower, 1/3 or negative 2/3? Well, obviously the negative number is smaller than the positive number. So when we divide x squared plus 4 to the 1/3 by x squared plus 4 to the negative 2/3, we get the base x squared plus 4 to the, and now we subtract the exponents. 1/3 minus negative 2/3 is 1. Minus the 2/3 x squared does not come out. It wasn't part of our common factor. And then x squared plus 4 to the negative 2/3 divided by itself leaves an understood 1 multiplied by that 2/3 x squared all over x squared plus 4 to the 2/3. Now then, that negative exponent means that x squared plus 4 to the 2/3, that needs to be brought down, and in the denominator it will be positive 2/3, and then you'll have x squared plus 4 to the 2/3 times x squared plus 4 to the 2/3. So our denominator, to multiply those powers with the same base, we will add the 2/3 from the one coming down plus the 2/3 from the one that's already down in the denominator. So that's 4/3. That's the denominator. And then in the numerator, we'll have x squared minus 2/3 x squared, which is 1/3 x squared plus 4. Then the last step would be, we should never leave what we call a complex fraction, a fraction that has fractions in it. So I'm going to multiply this fraction by 1. The form of 1 is the common denominator of all those little fractions over itself. The only little fraction in this problem is 1/3. Its denominator is 3, so that is our common denominator because it's the only denominator we have. And if we multiply that fraction by 3 over 3, we get x squared plus 12. Make sure you distribute that 3 to every term, over 3 times x squared plus 4 to the 4/3. And since that's 4 over 3, I will not take this back to a radical form. I will leave it like that. It's not that it's wrong to take it back. I'm just going to say that you need not. Unless it had become 1/3, we would have rewritten it as a cube root radical. Okay, let's look at the next example. Y is equal to 3x minus 1 over x squared plus 3 quantity squared. And although we could do the squaring first, which would not be that hard, and then use the quotient rule to do the derivative of what's left, I want to pretend like that weren't squaring, but some really big power, like to the 23rd, which I would not want to do that algebra of multiplying that by itself that many times. So I'm going to pretend like we have to use the what would then be the only option would be the general power rule and the chain rule. So dy dx, the outside function is something squared. So the derivative of something squared is 2 times that something raised to the first. You can ignore my writing that as the first. You can do that in your head and just leave it without that 1 written if you want to for right now. But I'm doing it for clarity. Times the derivative of the inside function. And this time, because it's kind of complicated, I'm going to actually write out that that's the next step, is to do that derivative of this kind of complicated inside function. Okay. That last thing, d dx of that, is usually what I just say in my head is the derivative of the inside something, and that's what I get. But I think writing it down when it's more complicated will save you the bother of thinking, oh my gosh, what comes next? How do I do that? Because if you try to keep too much in your head, you're going to make mistakes. Okay, now the inside function itself is a quotient, so its derivative will be found using the quotient rule. So that's going to be low d high, the derivative of the numerator is 3, low d high minus high d low, and the derivative of the denominator is 2x squared. I'm sorry, 2x, my bad, plus 0, 2x plus 0, all over the square of low. So low d high minus high d low, all over the square of low. And now we have some simplifying to do. Let's see. I'm trying to decide what order I want to simplify this in. I think what I'd like to do is work on that quotient rule answer. So I'm not going to do anything with the first two entries just yet, so that we can make sure that that's as simple as we can make it. So that's going to be distributing 3x squared plus 9 minus 6x squared plus 2x. Make sure you're distributing both the negative and the 2x in that second half of the fraction there. You have to be really careful with your algebra. Okay, now let me see. So it looks like I have 2 times 3x minus 1 over x squared plus 3 multiplied by negative 3x squared plus 2x plus 9. And I need to check to see if that quadratic polynomial factors or not. And if you remember the discriminant test I showed you before, b squared minus 4ac is 2 squared minus 4 times a, which is negative 3, times c, which is 9. Okay, and that's, well, I'm going to use my calculator so that I don't make any mistakes. I was about to do it in my head, and I decided to chicken out because I don't want to have any errors in stuff that I'm presenting to you. Okay, that's 112. 112 is not a perfect square. That means that that trinomial is prime. And so we don't have to worry about it. It doesn't factor. Okay, so our final answer is going to be 2 times 3x minus 1 times negative 3x squared. And again, I'm doing this in factored form on purpose because of what we're going to be doing with the first derivative answer soon. So it is important that you are getting the idea of factoring because it's extremely important. And if you're having trouble factoring, you need to go back and work on this some more. We need to talk about it maybe in class or something to help you get better at that, because really, to me, that's one of the harder parts of calculus is all of the pre-calculus notions, meaning every course before calculus. Like algebra and pre-calculus and all that. That's stuff that you're still supposed to know, and you may have forgotten about it. Okay, so that's the final answer on that one. Now, for the trig functions, the chain rule versions of those is if you have the sine of something, the derivative will be cosine of the something times the derivative of that something, which is just the chain rule. And so if you look at the next page where it has all of these chain rule versions, that's basically what it is you will do the outside function as the trig function, and the inside function its derivative will be multiplied by the derivative of the original function evaluated at u. And so I'm not going to read all of those to you, but that's the chain rule version of those. So let's do some examples of that. Example A, y equals sine of 2x. In fact, this may be the one we did earlier. Exactly. Oops. Forgot to write the sign. It may be something we've already looked at, but that's okay. Won't hurt anything. The outside function is sine of something, so its derivative, dy dx, we're going to take the derivative of the sine of something is cosine of that something times the derivative of that something, and the derivative of 2x is 2. I'm going to put that 2 out in front on purpose, because if I see cosine of 2x times 2, might I accidentally think that that's supposed to be the cosine of 4x? And that ambiguity, is that what I meant? Or did I mean that that's equal to 2 cosine of 2x? Those are very different things. Pick any random number you want and put cosine of 4 times that number in your calculator, and then do 2 times cosine of twice that same number in your calculator. Don't pick anything really trivial like 0. Probably would not be that. Well, 0 actually would be good. But anyway, sometimes you don't want to pick easy numbers like 0 or pi or something like that that's really obviously might have some exceptional equalities there. This one is wrong. Anyway, in this, it's always the whole thing, cosine of 2x, that's being multiplied by 2, and you should put that 2 out in front. And you can confirm that for yourself in the calculator. Those are not the same. And so, generally speaking, any number being multiplied by the cosine or whatever trig function, you should put it out in front. Okay, next one. If y equals cosine of x minus 1. So we've got the derivative of cosine of something is what we're looking for. So cosine is the outside function. The derivative of cosine of something is negative sine of that something times the derivative of that something. And the derivative of x minus 1 is simply 1. And so I'm not going to write the times 1, because that would mean I have to write another line in my answer. If it had been some number, I probably would have wanted to put it out in front. So it would be a negative number, sine of whatever, but it isn't. So that one's done. And then y equals tangent of 3x. So this is the tangent of something. Okay, the derivative of tangent of something is secant squared of that something times the derivative of that something, and the derivative of 3x is 3. So notice I'm leaving some space because I know what's coming, and you'll get better at that the more of this you do. So I'll leave that space so there's a place to put that 3 without squeezing it in. And so anyway, that's the answer to that one. So, the very last slide is a summary of all the differentiation rules. And this one, they're writing them in terms of u, where now u can be any inside function. For example, the constant multiple rule. The derivative of the constant times a function is still the constant times the derivative of that function, the inside function. So these are just in terms of u. Instead of being like c times x, it's a more generic thing. So anyway, these are all of the differentiation rules that we've learned so far, and you're responsible for knowing all of them. So make sure that they are committed to memory and at your fingertips when needed. All right, that ends this lesson. I will see you in class.